VSSP. Today we have Ms. Sangeeta Pakhare from ICER Trivandrum. She is doing her PhD right now. PhD, she is in third year. So I'd like to invite her.
Okay. Thanks for the introduction. So we'll be starting with today. Today's speaker is Vishavjeet Rai. He's from RJ College, Mumbai. He has attended level O, and today's topic for him is representation of numbers as difference of squares. So yeah, Vishwajit, over to you. You can present your screen.
Okay, thank you. Hello everyone. We will be talking about a representation of numbers as difference of squares. So, like means if I have an integer, let's say m, then will I be able to write always like m something like a square minus b square, where a and b are some integers again. So this will think about which are the numbers we can write in this form. Okay, so before that we will see some one small result which will be going to help will in this proving. So if I have an integer m, then m under modulo 4. So we say a is congruent to b modulo 4 if and only if 4 divides a minus b, right? So here we consider if m is an integer, so there is only two possibilities. Either it is an even number. In that case, if m is an even number, so we have an if the m is an even number, in that case there will exist a k in Z such that how can I write m equal to some 2k. So m square will be nothing but 4k square. So this is again a multiple of 4. So I can say m square is congruent to 0 modulo 4. Okay. Now case 2. If I have m to be an integer number, sorry, m, if I have m as an odd number, in that case I can write m as 2k plus 1. So it will be m square. This is nothing but 4k square plus 4k plus 1. This is something like multiple of 4 plus 1. M square is congruent to 1 modulo 4. Is it clear?
Yes, it is clear.
Okay. So if I suppose, so here we are done. If I suppose I have an integer m which can be written as sum of difference of squares, in that case, like I know that a and b both are integer. So from the previous result, I can say a square is congruent to 0 or 1, right? Similarly, b square will be congruent to either 0 or 1 modulo 4. What I can say about like a square minus b square? There are like different possibilities. Na? A square can be congruent to 0 or 1. B square can be congruent to 0 or 1. So one of the case will be a square is congruent to 0 and b square is also congruent to 0. In that case, I will have a square minus b square. This will be congruent to 0, right? Else, other case, if a square is congruent to 1 and b square is congruent to 0, in that case, I'll have a square minus b will be congruent to 1 modulo 4. Third possibility is both are congruent to 1. In that case, again, I will get 0. And the last possibility is if I have a square congruent to 0 and b square congruent to 1. In that case, I will get minus 1, but this is same as 3, right? So there are three possibilities. Sorry for the writing. A square minus b is either congruent to 0 or 1 or 3 modulo 4. So we see if I have an integer, if I am able to represent it as a difference of squares, in that case, it can't be of type 4k plus 2. Like it can't leave a remainder 2. So that means our result says if m can be represented as difference of squares, then m, this is m, no? So m is either congruent to 0 or 1 or 3 modulo 4, right? So the next question arises, is converse true or not, right? Sorry. Is converse true? Okay. So Wilson, here I'll make an observation. Like if I consider all the squares, like 0 square, 1 square, 2 square, 3 square, 4 square, 5 square, and so on. Then 0 square is same as 0. 1 square is 1, 4, 9, 16, 25. What will be the difference of these consecutive numbers? 1 minus 0 is 1, and these two, it will give 3. 4 minus 1, right? And this is 5, this is 7, and this is 9. So I am getting, I can write this one as 1 square minus 0 square. This 3 as 2 square minus 1 square. Similarly, 5 as 3 square minus 2 square. In this manner, I can write every odd numbers as a difference of squares. So if I consider the above question, like is converse true or not? So if I have an integer m, which is not of the form 4k plus 2, that means it is congruent to either 0 or 1 or 3. In that case, like it is of the form 4k or 4k plus 1 or 4k plus 3. These two cases we have covered in this. Like, so if I have an integer of this form 4k plus 1 or 4k plus 3, that means it is an odd number. So odd number I can represent in this manner. Again, if I take difference of these two numbers, like 4 minus 0, then I'll be getting 4, and here 1 square and 3 square difference means 3 square minus 1 square, I'll be getting 8. And here if you observe, this is nothing but 16 minus 4, this is 12, and this is nothing but 16, right? 10. So I can like see here we are getting all multiples of 4, 4, and they are of form 4k. So we are covering all the multiples of 4 also here. So if I have a number which is of the form 4k, I can represent it as a difference of squares. So, but now we need to generalize it how like we can prove it. So if I have a number m in integer which is not of the form 4k plus 2, in that case it will be either these two form or this one, right? So if I have these thing 4k plus 1 or 4k plus 3, so can anyone relate this? Like if I have an integer, say here it is an m, then what should I choose? Like this thing. What should be here and here from this observation? Like here I have 1. I have written it as 1 square minus 0 square. Here I have 3. I have written it as 4 square, 2 square minus 1 square, right? Here 5. So 3 square minus 2 square. Yes, anyone? Okay, so see here. 1 is nothing but 1 square minus 0 square. 3 is nothing but 2 square minus 1 square. 5 is nothing but 2 square minus 2 square. So this number is nothing but in between these two here. But another way, this 5 I can obtain by 3 into 2, right, minus 1. And this is nothing but 2. I can 2 into 2 plus 1, then I'm getting 5. So if I have 5, then here it is 5 plus 1 divided by 2. So here I can write m plus 1 divided by 2, and here I can write m minus 1 divided by 2. So if m is odd, in that case m plus 1 is any one number. So m plus 1, this belongs to integers. This also belongs to integer. So this way we can represent. Right. So if m is n, here case 1. If m is of the form 4k plus 1 or 4k plus 3, in that case, I can represent m as a difference of squares in this manner. Next, case 2, if m is of the 4k, then I can write m equal to m upon 4 plus 1 square minus m upon 4 minus 1 square. Right? So if m is a multiple of 4, then m by 4, this is an integer. Right? So this way I can represent. So if you expand it, you will get m. Now, we'll be going to see some one application of this. Like before that, we will see some one result here. Like every odd number, I can represent as a difference of consecutive number, difference of squares of consecutive numbers. Here the thing what I'm getting, m plus 1 by 2 and m minus 1 by 2 in this case, right? So these are consecutive. So m plus 1 by 2 and m minus 1 by 2. If this is odd, then these are consecutive. So every odd numbers can be represented as two consecutive numbers. So we have seen that every odd number can be represented as difference of two consecutive numbers, right? So like one thing, if I have m, right, m as a square minus b square, what we like from even 6th 7th standard, we have whenever we see a square minus b square, we usually do this thing, right? So I can say this a plus b and a minus b. b, both are factors of m, right? So this theory helps us to find like factors for any integer, positive integer. So this will be going to say in next few. So like if I have before that, if I have prime, sorry. See here, if I have m is something like a into b, some product of two numbers. Okay, so one way is to write m as d plus d. Sorry, what I'm writing. Uh, a plus b by 2 whole square minus a minus b divided by 2 whole square. Okay, but this thing I can do only when this a plus b is an even number. So there, if I can write, if I have m as a into b and both have same parity, means a and b both are odd or both are even simultaneously. In that case, I can write m as in this way: a plus b whole square upon divide. Sorry, a plus b by 2 whole square minus a minus b by 2 whole square. But see, in that case, if I have suppose p, so one theorem is like if I have prime, then this representation is unique. We have seen every odd number can be represented as a difference of two consecutive squares. Consecutive squares. It should be consecutive squares. Consecutive squares. Squares of consecutive numbers. Okay. So consecutive squares. So then P. Let's say let's say P be a prime now. P be an odd prime. P be an odd prime. Then if I am able to write p as a p equal to some a square minus b square, in that case this is nothing but a plus b, a minus b. We are here assuming a greater than b, obviously. So this is nothing but, what is so special about p? It is a prime number, right? So p into 1 I can write, and then it has two factors here, a plus b and a minus b. So this implies a plus b is nothing but t and a minus b is 1, right? So in that case, if you solve these two equations, then you will get a equal to p plus 1 by 2 and b equal to p minus 1 by 2. So these are also consecutive, right? So every prime, if we have a prime, then I can represent it as a difference of two consecutive squares uniquely. So this expression is unique. Okay, so for prime.
Yeah.
But yes, sir.
Doubt here that
Uh,
a minus b also can be p, right? Or it can't be.
sorry, a minus b.
It can be p or not.
No, sir, because like if I am assuming a greater than b, obviously
Yeah,
a,
okay.
so a plus b will be greater than a minus b. In that case, we are getting in this way. So next, so this representation is unique for prime. So here is one task for you: find a composite number whose this representation is not unique. This representation is not unique. Means you have to search you have to search a number. Obviously, it will not prime, because we have done for prime that means odd prime. It will not be a odd prime. So it will not be of the form also 4k plus 2, right? It will not be a prime. And I can represent it as a square minus b square, also some x square minus y square, but these two are consecutive. So two different representation we need. Now we go for factorization. Like we have already seen, if I have m as a square minus b square, so this technique helps us to find the factors. So this is famously known as Fermat's factorization method. So suppose we want to discover like what are the factors for a given number, given positive integer. So how can we like approach this problem? So if we are given a like big number, then how to factorize them, right? So if I am equal to a plus b, so in this manner. So the problem arises like if I have if somehow I can write m as a square minus b square, then obviously these two things will be a factor for m. So our problem shifted to finding solutions for this thing. M equal to a square minus b square. Will there be means finding our main motto is now to find a and b such that I can represent m like this. Okay. So okay. This is seem to find m to be. I find I can write this as a square minus m equal to b square, right? So we are known m is known to us. We are searching for a and b. Okay. So as b is some any means positive integer we are taking here. So otherwise also this is a positive number. So this should be a positive number. So our technique is to find like a square minus m is some positive number. Even means it can be 0. So in that case, one thing. Okay, let's start with this only. So a square minus m is greater than equal to 0. So a is nothing but greater than. We are taking positive. We are considering positive square root only here. So we consider this. We take a means here we are getting a greater than equal to m. So we try to search for like we this is known. This is known to us. So we take some k equal to root m. So we take greatest integer value like plus 1 we add. So we are getting whatever be the number this is. So greater than that integer we are considering, and we will check that whether k square we will putting in this equation k square minus m. This is a perfect square or not. So if it is a perfect square, then it will be some b square. So in that case, we will be able to find factors. This thing we can go reverse way. So if this doesn't happen, in that case we move on and k plus 1 we check. K plus 1 square minus m, is it a perfect square or not? This process we can continue, right? Ultimately we will get what is the guarantee that this step doesn't miss this process will end up. So like we have already one representation, so we are here assuming one thing now. If I have any number m, so we can extract all the powers of 2, whatever the factors of 2 is there, we can extract it from them. So m will be nothing, so that's why we are considering here m only odd number. There is no meaning of like we have two factor there. So that's why we are looking for m as the odd integers. So if m is an odd integer, then I know m is nothing but m plus what representation? M plus 1 by 2 whole square minus M minus 1 by 2 whole square. This is nothing but this is same as M plus 1 by 2 whole square minus M equal to M minus 1 by 2 whole square. So whenever we proceed, we go, then ultimately we will touch this M plus 1 by 2. So after all, like we will end up with this. So that's why our process will stop after some finite step. Our process will stop after some finite step. So this way it helps us to find the factors of. So we'll do an example for this. So can you give me some like big numbers, 4 or 5 digit only? Yeah? Yes. Hello. Someone please give a like 4 or 5 digit number. We'll try to find the factors for that one.
Take today's date.
Sorry, not able to hear you.
Today's date. You can take it.
So let's check. Okay. To 911, then what will the square root around? I'm getting 53. So this is nothing but something like 53.95. So I can choose K to be 54. So if I have K 54, in that case, K square minus N means 54 is square minus my number 2911. So this will be 54, right? So 5. So this is nothing but 5. So it is not a perfect square. So here we will proceed with 55. So if we have 55, then we are getting 114. Okay, 55 square minus 2911. So this we are getting 114. This is again not a perfect square. And if we do for 56, in that case, we are getting 225. 55 square minus 2, sorry, 2911. This is nothing but 225. This is nothing but 15 square. So this is a perfect square. So I can write 56 square minus 1 to 50. These two are original thing. 56 square minus 15 square, but this is nothing but 56 plus 15 and 56 minus 15. So this will give us 11, 46. Seven into 141, right? So this way we are getting 71 and 41. These two are obviously these are primes actually. So we can't reduce further now. So these two are 71 and 41 are factors for the factors of
Vishwajit, there is a time bound.
Yes, ma'am.
You can wind up. You have
Yes,
more
ma'am.
2 to 4 minutes.
Complete. It's completed, ma'am.
Okay. In the audience, is anyone having any doubts or any questions? Yeah, I think we can thank our speaker. Thank you so much, Vishavjeet. It was a good presentation. Hopefully now whenever we look at this topic, we'll think of the presentation which you gave. It was really nice.
Thank you, ma'am.
Yeah.